All right, we're going to move on to the last part of Chapter 4, which gets into computing, doing system reduction is what it's called, and computing resultant forces and moments. So here's what I want you to contemplate here. So going back to these levers that I've played a bit with, so suppose we have the following. If I had a lever with a force out here, and I could have something with a lot of forces, and the same idea would apply, so I'm just trying to keep life easy. If I had this mechanical device, and here I pretend I have lots of forces here, in this case I have one, here's the idea. I can reduce this force down to a resultant force in a moment at one point, namely O. So I can take this force and I can replace it with an equivalent resultant force right here at O, plus a pure couple moment, which is equal to F times D. Let that distance be D. So this force and this force here, which presents has a downward force, and combined with this moment, they do the same thing. These are equivalent. If I saw this or I saw that, the same thing would happen. That's the point. Now, so in the world of reduction, picture we could have a whole bunch of forces all out here, and moments and all sorts of stuff, and I could move them down to one resultant force and a moment at this point. So that's the point we want to get across. You can reduce a bunch of stuff at one point to a force in a moment. Okay. By the same token, if you have a force and a moment at one point, you can reduce it down to a single force. So you could actually go back this way and say, oh, well, I have a force and a moment. I could simply move this force out to a distance such that we'd get the same moment here. So I can go back the other way. This is called system reduction. Really all this is, it's preparation for summing forces and moments for rigid body equilibrium. All right? So that's the point but anyway, just to understand, you can have a whole pile of forces and moments, reduce them down to a single force and moment at one given point. And if you have a bunch of stuff at one given point, you can effectively move it out and reduce that down to a single force at some single point. All right. So this sets up our an example. And so let me draw what we're going to be playing with here. So I have a beam coming out of the wall. Like so. And A is at the center of the beam where the beam joins the wall. And let's see, I'm going to take this, that'll be a point, quote unquote, 2 meters out. And at this point, we're going to have a force come in on the top surface at 60 degrees. And that will be 30 kilonewtons. We will go one more meter, and in the center of the beam, right here, we will apply a clockwise, let's take this down out of the way, 45 kilonewton meter torque. We will go another meter out, and we'll have a support on the beam. And this is, being a roller, it only exerts force if we were to look at the force vertically. And then we will go 2 more meters out, and that will let that be the end of the beam. So taking all this out. So take a big saw right there. And on this top edge, we will have a force come in of 26 kilonewtons, where this is a 11.5, and then on the hypotenuse would be 13 triangle. No, 12. It's 12. 5, 12, 13. So 12 squared is 144 plus 25. 5 squared is 169, which is 13 squared. All right, and we will have the thickness of our beam be 0.6 meters. And down the center, we'll call that the x-axis. And so we'll let that be y going up there. All right, so what we want to do for this system we have here, we're going to problem part 1 is find a resultant force and moment at A. All right. Now, I hate these problems. This is my most hated part of the course. We need to be able to sum forces and moments. I think this is really confusing. So this problem says find the resulting forces and moments at A. If you were doing this in a real problem, summing forces, you would take this support out and replace it with a vertical force supporting the beam. This makes no sense at all. As an academic exercise to sum forces and moments, in that sense, it makes sense. In terms of real practice, this is stupid. Okay? I'm being blunt with you. This chapter is bizarre in talking about this stuff. Anytime I sum forces, I take away all the supports. I take away the wall. I put in stuff for supports for the wall and start summing things around. This is selectively just choosing some of them to sum as a sum is beyond stupid. Nobody would do this. This is simply an academic exercise preparing for when we do chapter 5, which is rigid body equilibrium, where we have to sum forces and sum moments. So as we're doing this stuff, only take it as an academic exercise. This has no meaning in the real world for what we're doing. Okay? Keep that really, really straight. All right? Because we're going to sum this, this, and this at A, but we're not putting in wall supports. The wall's obviously helping support and to keep this up, and we got a support out here, and we're ignoring them. This is wrong. Other than if we want practice adding what we have. Okay, so I do these, this is part of the required curriculum. I do this with some level of trepidation, and I'm trying to be honest with you. I hate this. It just strikes me as beyond stupid. I think I could cut this out and we'd be fine, but I can't. So please keep that in perspective. So, summing the forces. There are 2 of them. Sum them. Summing the forces in the x. We have 30. That would be cosine of 60. It's going in the negative x direction. Minus 30. Cos 60. Done. This is going in the positive x direction. Plus 26. Our units are obviously kilonewtons. That's fine. I don't object to that. And that would be 5 on 13 is the x. So we have the hypotenuse is 13, so the cosine is 5 over 13. No problem with that. Add them up, come up with minus 5 kilonewtons. So the net is going that way. Okay. Summing in the y. That's going down, that's going down. No problem. Minus 30. Sine of 60. Minus 26. 12 on 13 gives me minus 50 kilonewtons. Okay, fine. So we would have a resultant force at A that had basically put a force right in here that's coming in at minus 5 and minus 50 kilonewtons. That's what it's setting up. Now, summing the moments at A. All right. This is considered a couple moments, so it applies everywhere. So let's see. That's going clockwise. No big deal. So we have minus 45 that we'll toss in. Done. Now let's take a look at this one. Notice here, this is subtle, A is in the center of the beam. It's along the center line. This is applied at the top. All right, so what I have now is I have a force coming in, like so, and then there's another force coming in on the top surface. That will exert a small moment. So let's see. So if we look at the y component, let's see, which one do I want to look at first? Yep. So the part coming down here, so I have coming down is 30 sine 60. Okay, that's the y component coming down. And then the horizontal, that's the vertical. Then we need a horizontal distance, that's 2. Now we ask the question, if a force is coming down relative to this, what does it want to do? The force going down, that's clockwise. Put in a negative. Done. Now we have the horizontal portion. It's going in the negative x direction, which really doesn't bother me. So I can just move it over to here. It's going this way. Relative to A, it's going to go counterclockwise. So that's positive. So I have plus 30 cos of 60. And the moment arm is, if this is 0.6 thick, A is in the center, 0.3. Done. Now I have this thing. The y component right here. Let's see, that's 2, 3, 4, 5, 6 out. So, and it's going clockwise, so I'll have a minus 26. The y component is 12 over 13, and it is 6 out. Done. Now I have an x component going this way. Relative to A, it'll be clockwise. So that's another negative. 26, the x component is 5 on 13. Thickness of the beam, 0.3. Yep. And so now it's just a calculator exercise. We come up with minus 239.46 kilonewton meters. And we'll note negative clockwise. Okay? You don't need to put in the clockwise. All right. So that's part one. And so that's summing the things that are existing at A. Why wouldn't you include that? It's stupid. But anyway, for what it's worth. Here's what you would normally do. You take this out, include the force that's here, then all these forces tell you what A must counteract for this thing to be stable. All right? So, yeah, if you wanted to say what are the forces required and moments required to hold this beam up here at the wall, sum this, sum that force for that support, and that force there, and bam, you'd have it. That would make sense. This is stupid. But nonetheless, we go on. Part 2. So for part 2, we want to take this. This is the resultant of these three things, bizarrely missing that one, at A. So for part 2, we're going to kind of put our reduction stuff to work. So we're going to take these forces and moments, which would be applied at A, and we're going to find a single point where we could have a single force, namely this one. So that's known. Where could we apply this force and at the same time achieve this moment? And so we wanted to find, so part 2 is reduce to single force, and force is a vector in x and y. So this is minus 5k along the x, minus 50 along the y. That's all one force. So that's not two forces. We consider that one. Reduce to single force at beam surface and beam center. So we're going to do this twice. is the bottom line I want to get across here. All right, so force is minus 5x minus 50y kilonewtons. So we want to move that force someplace where we achieve this. Well, that's not too hard to do. So let's just draw the beam. And so I want to apply basically, we'll just draw this in here like so, F. Where can I apply this force such that times this distance d, I get the same moment here? All right. And then, so that's kind of part 2A. Part 2B is find a spot in the middle of the beam where I can apply that same force, and I'd get the equivalent moment. Well, B's easier, so let's just do that one. So you're going to get to, there's some distance d to get to A. So the y component of the force is 50. So 50 times d equals minus, we can just ignore the sign for now, 239.46, solve for d. And that would be 4.79 meters. So if I had a force that was minus 5x minus 50y applied at the center of the beam, 4.79 meters out, that would be the equivalent of this force, that moment, and that force. It would have the exact same effect. For what that's worth, I don't know, but it's true. Okay? Now, we have the same problem here, except it's at the surface. So it's a little bit more involved. Okay? So now I have, so we have a force coming down, 50. That would be, so again we're trying to get to 239.46, and let me just use signs this time, so negative. So the force coming down is 50 times d, this distance there, 50 times d, all right, and then we'd have a horizontal portion, and its horizontal distance is 0.3, and that is going counterclockwise, so I'd have a plus 5 times 0.3 in there. Solve for d this time, it's a little bit bigger. Now, by the way, I've dropped a negative sign here. This is minus 50. This part here is going clockwise. All right. Solve for d, get 4.82 meters. And so, because this is because of this term kind of works against us, we have to be a little bit farther out. Again, not sure what this is useful for, but mathematically it's certainly true. All right. Okay. One last problem for chapter 4 that we're going to take a look at. And we're just going to do this very quickly. I'm not going to put a lot into this. So this is just a problem using what I kind of wish we hadn't learned. So what this problem is going to say is find resultant force along AB measured from B. So let's just, too much information here. So I have this fence postish kind of weird thing. It's 3 meters high with this funny little precipice coming off here. Why? I have no idea. So we have 1 meter, 2 meters, 3 meters to the top surface. This thing is 0.4 meters cross section with this extra piece added on. Again, why I don't know. And so AB, A is in the center here, so it would be 0.2 meters here, 0.2 there, and going straight vertical, we would hit B. So B from here to there would be 0.2 meters as well. So what we want to do, and notice there will be forces and moments associated with the support. We are ignoring them. In the real world, when you're trying to figure stuff out, you wouldn't ignore them. But in this chapter, we ignore logic. We're going to do it their way. So this is wrong, but for educational purposes, we are summing things together. So let it happen. Okay? Just let it happen. All right. So we're going to sum this, and that, and find a resultant at B. Okay, at B, and then we're going to take that resultant and move it along a line measured from B. So we're going to find some place, say here, where we can replace this, that, and that by one force. That would achieve the exact same thing. Okay? So, hopefully we understand it. Now do it. And note, this is 0.2, so this distance here is 0.3 meters. 0.2, 0.2. See, from here to the outer edge is 0.5, so that's a 0.3 extra to get there. We'll just note that. All right. Once you understand the problem, this is conceptually really simple. So we simply sum the forces, and they apply everywhere. So summing the forces, we have, this is 500 newtons right here. This is 30 degrees up, so cosine 30, that's in the negative x direction. Here we have 250. This is a 3, 4, 5 triangle, so the x portion is 4/5. So I have a 250 times 4/5, and that's just pointed in the negative x, so I subtract off 300. Don't have to put a lot of thought into that. And I'll make this a little bit bigger for you. Summing in the y. This has no contribution. This is 500 times sine 30. Bam, going up. This is 250, 3/5 of it going straight down. Minus 250 times 3/5. Add them together, get net 100 up. Done. Now, so we could put these two forces, remove this, remove that, and put a force here at B with this x and that y component. If we did that, we'd also have to add at B a moment. Now we compute that. So we're going to compute the moments of all these things. All right. So if we look at this, here we've got 500. If we take the x component, 500 cos 30, its distance down is 1 meter, and it is trying to, relative to B, to go clockwise. So we have minus 500 cos 30, the x component, the y distance, negative, done. If we tried to go up with this thing, relative to B, it would go clockwise. So we have minus for the clockwise, 500 sine 30, the y component of the force. We need the x component direction, that's 0.2. That's right there. All done. The 250 Newton force. The x component goes along this line, which is aligned with B, so there is no torque. We only have the y component, which is 250 times 3/5. Relative to B, a force going down here is trying to go clockwise again. So 250 times 3/5 is the force. 0.5 meters is the distance from B to where the force is applied. The negative for the clockwise. Done. Minus 300 newtons. All right, we can move that over into the center. It's going this way, and it's 2 meters up, and it's going clockwise. So we have a minus 300 times 2, add it all up, minus 1158 newton meters. So if we put this xy force here and a moment there at B, that would be the equivalent of these three things. Still need to consider what the supports are doing, but that's irrelevant. All right. Now, from here, the question says, find a single force along the line AB, measured from B, where you could apply this single force, this one right here, in the x and y, and it would achieve the same effect as the moment. All right. If we put a force being applied along here, we'll notice the y component will be aligned with B, so it will do nothing. All that matters is the x component and that distance. So here's 1158, that's the moment we need. 533, that's the x component. What's the distance? Solve for D, 2.17 meters. All right, and so here we have the answer. F resultant is minus 533x plus 100y newtons, 2.17 meters down from B along AB. Problem finished. And we won't do any more of this. And that finishes up chapter 4. Next up, we're going to have a short discussion on why we're going to do chapter 9 next instead of 5. I do not agree with the ordering of the chapters in this text. We'll talk about that soon. Bye for now.